So temperature is a large part of what we have to pay attention to in flight planning. One of the clips I like to show is this anti-icing, de-icing clip. When you have a wing and you have ice accumulating on the wing, this can be really, really detrimental to lift, and actually increases drag quite a bit too. And so what they have on commercial aircraft is this de-icing fluid. And if you've ever traveled up north in the wintertime and there's any sort of precipitation or clouds, you're going to get sprayed down with this anti-icing, fluid. And so, yeah, and so really when I was doing flight planning up in Charlotte, when I was flying up there, we would have to pay very close attention if the temperature was really 2 degrees Celsius or below, all the way down to -20, which wouldn't get that cold, but we would, we'd have to assume that there's definitely icing possibility, and plan whether to go or not based on what the weather looked like. One of the things I like to show too is with the states of matter. And you can, get this clip if you type in PHET, P-H-E-T, and then do states of matter. You can find that simulation and you'll see, the different states of matter, and it's good to see that structure. And I like to show that. So temperature kinetic theory is what we're going to do as we establish our foundation for our understanding of thermal physics. And way back in 1827, Robert Brown looked at pollen suspended in still water and looked at that pollen and saw that it still moved. And so we know that atoms, in any substance are always in motion. And so even if things look still, we have the motion of the atoms, and then the molecules that are made up of the atoms. And so, in the states of matter, we're typically, used to seeing we have the solid state, as a kind of a set structure, then the fluid state, the molecules moving past each other. And then in the gaseous state, the molecules actually spreading out from each other. And so, if we think about the states of matter and think about the structure, we can think about, springs. And so we have the bonds between the particles. For fluids, the particles are free to move around, right? And so, and liquids can take the shape of the container, but gases themselves will actually spread out and fill the container. And that's what we see, in letter C over here. And so, more structure, a little bit less structure than the least structure with the gaseous state. So temperature itself is a measure of the average kinetic energy of the particles in a substance. And temperature itself, we can consider, and even if we think about thermometers, right? We have a tube, and then you have the liquid inside the tube, and this liquid, is going to be shaking a certain amount, right? So if it heats up, it's going to be moving around more. And temperature is directly related to kinetic energy, and we know kinetic energy equals 1/2 mv squared, right? So if we look at an average particle inside this thermometer, some may be moving faster than others, but if we look at an average one, then we would know essentially, what's going on with the temperature. And we'll be able to go back and forth from kinetic energy to temperature later. If we take a look at, a glass, right? We have a liquid inside this glass, and this liquid, let's say it's coffee or something, and it's going around. It's going to have a certain average kinetic energy, right? And so if we had, a glass of ice water, let's say, as compared, the molecules aren't moving around as much, and so this has a higher temperature, higher average kinetic energy for the molecules inside. So in a thermometer, we have the expansion of the material as the temperature increases. And, the mercury thermometer is the one that's typically been used, and they can still use mercury thermometers. You just have the risk of, if it breaks, you've got a mercury, and, mercury is poisonous. And so, usually in classrooms, we'll have either colored alcohol or mineral spirits as the, the substance that we use. So thermal equilibrium is where you have two objects at different temperatures in contact, eventually reaching the same temperature. And so, you have two objects that maybe one's at one temperature, the other's at a different temperature. They're in contact. Maybe this one is at 10 degrees Celsius. Maybe this one's at 5 degrees Celsius. And when they touch, eventually they will become the same temperature. And we know it's going to have to be in between these two, right? It can't be, all of a sudden this becomes 4 and this becomes, 11 or something, right? We know that it's going to have to be in between these two. So when we talk about the 0th law of thermodynamics, that's going to be an important consideration. If two systems are in equilibrium with a third system, they are in equilibrium with each other. And so with the 0th law, and they had to make it after already having the first and second laws, so this is kind of establishment. So in other words, if you had three things, let's say you had substance A, substance B, substance C, and you said that, okay, substance A and substance B are in thermal equilibrium, right? But then substance B and substance C are in equilibrium with each other. Then, the substance of C and A would have to be in equilibrium with each other. And so, yeah, and so it's kind of one of those straightforward things, but important to see there. So in a temperature gauge like this is a picture of a pressure and temperature gauge from an aircraft. And so when we did our flying, if we had a reciprocating type engine, we would keep an eye on the pressure. This is the oil pressure, and so it should be within the green range. And then the temperature, of the oil itself should be in the green range as well. What we would pay attention to is, let's say that the pressure all of a sudden was starting to drop and the temperature was starting to rise. That means that, there's probably a leak where, there's not as much oil in there, and then the oil itself is getting hotter and hotter and hotter. At that point, we would have to really consider, the integrity of the engine and try to land as soon as possible. And so looking at temperature with the oil is really important. So, we asked, why is it important to have a standard scale for temperature? And, why don't we have just something arbitrary like, we say it's a certain amount and just assume that? There's a lot of different reasons that we have, the standard scale. In the medical field, you have to be able to communicate, and so if you have a patient, a doctor needs to know from one doctor to the other what's going on in terms of their temperature. And if you have a standard scale, you're good there. Communicating weather, right? And so we have a way that we can understand the weather. We look at it in the morning, what the temperatures will be, and we can base, what we wear based on that. And then in science, if we're communicating, we need to be able to communicate our results. And so, we have to be able to replicate different experiments and really understand what's going on with the different experiments. And so, it's really the same reason we have the other kind of standard systems of measurement for communication and consistency. And so one of the things that we'll need to be able to do, and this is, kind of reality, we were dealing with Fahrenheit and Celsius. So if we, let's say we have a temperature in Celsius and we want to get it into Fahrenheit, you're going to take the Celsius temperature and multiply it by 9/5. And that's the ratio between Celsius and Fahrenheit. But the zero reference, right, is different. So once we get the conversion, the ratio conversion, 9/5 times the Celsius temperature, we add 32 to it to get the actual Fahrenheit temperature. And so if we go the other way, let's say we have Fahrenheit, we're going to have to subtract 32 first. And that's really important. You got to subtract 32 first and then multiply by 5/9 to get the ratio right with the temperature in Celsius there. So let's go ahead and convert this one. You can go ahead and pause the clip and try this, and then when you're ready to check, you can hit play to continue. All right, so we've got, temperature in Fahrenheit minus 32 times 5/9, and we should get 32.22 degrees Celsius for the Celsius degree. So, Yeah, so we started with 90 degrees Fahrenheit, and 32.22 would be that in Celsius. Let's go ahead and try this one as well. So go ahead and pause the clip and convert, and then you can check, hit play when you're ready to check. Okay, so with this one, we should get 167 degrees Fahrenheit from 75 degrees Celsius. Now, when we're heating metals, it's interesting. There's, as we heat up metals, metals expand. And so, depending on the kind of metal, we'll have different expansions. And so you've probably seen, on bridges, they have these little gaps, that you run over. And those are there because, you have concrete on one side, concrete on the other. And in the summertime, the concrete's going to heat up, right? And so as the concrete heats up, it's going to expand. And as it expands, if you don't have expansion joints, it's just going to crack. And so with thermal expansion, we're looking at the change in length. And in solids, it's mostly directly proportional to the change in temperature. So that's a really significant thing here. If we look at the factor of, let's say, we'll have the coefficient of linear expansion, right, alpha, and that is going to be the the greater alpha is, the greater the expansion we're going to have, because that's the coefficient of expansion. So when we calculate this, we multiply the original length, right, L0, that's the original length. We multiply that by 1 plus alpha times the change in temperature. Another way that we can write this is, the change in L is equal to alpha times the original length times delta T. And so we can look at that. And then again, alpha is the coefficient of linear expansion. The greater this value is, right, greater alpha is, the greater this change will be when we multiply it by L0, the original length. So let's try this example here. We have a concrete bridge, and the beam length is 134 meters, 15 degrees Celsius. What would the beam length be at negative 10 degrees Celsius? And we'll say for concrete, alpha is 12 times 10 to the negative 6th. This is the unit, by the way, for alpha, 1/degrees Celsius. You could technically have alpha in different units, and that would be fine as well. But yeah, go ahead and give this a try, and then when you're ready to check, you can hit play to continue. Okay, so we've got our value looking for the delta L, the change in length. So it's going to be about, well, we get a negative, right? So negative 0.0402, about 4 centimeters smaller than when it was cooler. So here's a list of different coefficients of expansion. And if you notice, there's two sections to this. We have the coefficient of linear expansion here, then we have volume expansion. And, we could look at the different values here. For instance, aluminum, right, for per degree Celsius, this is the linear, expansion coefficient, 25 times 10 to the negative 6th, which, looks like lead expands the most, right, at least with this list. And then aluminum would be second. And then quartz doesn't expand nearly as much, right, 0.4 times 10 to the negative 6th. And yeah, and so even with liquids, right, you go to expansion with liquids because it's not going linearly, right? Liquids will expand in 3 dimensions. And so, we've got that there with the different values. And so, as we continue forward here, we can use these, and this is what engineers will actually need to pay very close attention to in building. For instance, with construction of a bridge, right, they're going to have to pay very close attention to the types of, weather changes and how big their expansion joints need to be, for instance. And so, in any construction situation, they have to pay attention to the expansion